The title of this note is Complex Numbers, and the goal is to be able to plot a complex number, figure out its absolute value, and also write a complex number in polar form. So first, a quick refresher on complex numbers. In Algebra 2, you guys studied imaginary numbers. So remember that when you take the square root of a negative, it doesn't have a real answer, so we designate the answer as imaginary. Complex numbers are numbers that have a real part and an imaginary part. So we're going to write a complex number as a plus bi. We use the letter z to represent a complex number, so z is some complex number. And we can say it's a plus bi, or it could be a minus bi. So I'm going to put the plus or minus sign there. A is called the real part, because a represents a real number. And then bi is called the imaginary part, because it represents an imaginary number. So for example, I might have a complex number 2 plus 3i. That's an example of a complex number. It's 2 real plus 3 imaginary. Real numbers, like if I just had 2, that's considered a complex number because I could say it's 2 plus 0i. Likewise, any imaginary number, like let's say I have 3i, I can think of that as 0 plus 3i. So a real number is a complex number, an imaginary number is a complex number, and real and imaginary together are complex numbers. So basically, any number you can think of is a complex number. So how do you graph or plot a complex number? We're going to plot them on something that looks like the xy plane. But instead of the horizontal being the x-axis and the vertical being the y-axis, we're going to say that the horizontal is the real axis. So notice the label there. Whenever you're graphing, you need to label. It is no longer labeled x. It is now labeled real. And the y is no longer labeled y. It's now labeled imaginary. So if I want to plot the same number I have above, 2 plus 3i, I'm going to go to 2 on the real axis, 1, 2, and I'm going to go to 3, up 3 on the imaginary axis, and I'm going to put a point. That is one single complex number, 2 plus 3i. Once we know how to plot, then we can talk about the absolute value. So the absolute value of a number is how far it is from 0. The absolute value is your distance to 0. So if we think about this complex number, I'm going to pull the same one from the last slide. Let's use that same number. Okay, so we'll look at that stuff later. So here's the number 2 plus 3i. The absolute value is its distance to 0. Distance is the shortest straight line. So the absolute value of z is that red number. So how are we going to figure out how far that red segment is? Well, we know that we went over 2 on the real axis and up 3 on the imaginary axis. So what I hope you're seeing here is the right triangle, and we can then do Pythagorean theorem. Remember that that red part is the absolute value of z, so I'm using that notation for it. So then just applying Pythagorean theorem. So we have that this thing squared, the hypotenuse squared, or you can call it c, or I'm calling it the absolute value of z, equals 13. So then I'm going to take the square root on both sides. So the absolute value of z is the square root of 13. That's how far that number is from the number 0, which is still at the origin. So the Pythagorean theorem is going to be our formula. That's what I have here. Absolute value, when we're talking about complex numbers, has a special name. It's called the modulus. So the modulus is just the absolute value, and you take the x squared and the y squared. You can drop the I because the I just tells you that it's going up or down in the imaginary direction. Its length right up here was 3. So you just take the x value squared plus the y value squared, and then you take the square root. So try this one. Hit pause. Try to find the modulus of z equals 2 minus 5i. I want you to hit pause for a second. Try that one, and then when you click play, I'll have the answer up here. The last thing we're going to do in this set of notes is we're going to convert complex numbers to polar form. So we're going to use this example here. Z equals 1 minus I the square root of 3. So if we were to plot this, we would go over, this is the real number line, this is the imaginary number line. We would go over 1 and down radical 3. Down because that's negative in the I direction, and you go down radical 3. So there's that point right there. So remember, a polar number is in the form r, comma, where the radius of the circle is from the point to the origin. Notice that's the exact same concept as the modulus that we looked at earlier. It's Pythagorean theorem. That triangle has a length of 1, that leg. This one has a length of radical 3. So applying Pythagorean theorem, we get 1 plus 3 equals r squared. 1 plus 3 is 4, so r is 2. Now we need the angle. It's that angle right there. We're going to use the reference angle. I'm going to put the reference angle in green. Okay, that's the theta reference. So I know that the opposite leg is radical 3, and the adjacent leg is 1. So I'm going to use my inverse tangent ratio of opposite over adjacent, or y over x. We've seen this formula come up in multiple topics now. And so going to my calculator, I'm going to type the inverse tangent of radical 3. Okay, so there are some formulas that you're going to need. And we've seen these formulas in other chapters. There's the formula for the radius. It's the Pythagorean theorem. It's the same formula as modulus. And then to find the angle, we need that inverse tangent. That's just another way of writing that formula. So what if we're going to go the other way? These other two formulas are for going the other way. We saw them last unit. We're actually going to do those on the next page. So on the next page, we're going to convert numbers from polar to rectangular. So we're going to take this 3 pi over 4, which is in polar form, and we're going to convert it to a complex number. So actually, this text isn't right. How do I convert? No, that is right, from polar form to rectangular form. Okay, so we're going to convert it to a complex number. And so we need the x and the y, and we have the r and the theta. So we know that your formula on the previous slide says cosine is x over r. Multiply both sides by r, you get x equals r cosine theta. That formula should feel familiar. Y equals r sine theta. X is always cosine, y is always sine, no matter what unit we're in. So the x-coordinate is going to be 3 times the cosine of pi over 4. And the y-coordinate will be 3 times the sine of pi over 4. Because we know our unit circle, we know that the cosine of pi over 4 is 3 radical 2 over 2. That 3 is coming from right here. And then sine of pi over 4 is also radical 2 over 2 times 3. We're just going to stick it in the numerator. So the complex number z X represents horizontal, or the real part. So the real part is 3 radical 2 over 2. Y represents the vertical, or the imaginary part. So the imaginary part is also 3 radical 2 over 2, and you put an I with it. So that is the complex number in rectangular form with the X and the Y. So we're going to stop there and go ahead and draw a line for your notes and come into class ready to convert complex numbers.